Welcome, everyone. In this session, we'll tackle an interesting coding challenge, problem number 1652, defuse the bomb. This problem involves working with a circular array and an integer value, k, to transform the array into a new sequence. It's a great example of applying array manipulation techniques and understanding constraints to optimize your approach. Let's get started. In this problem, you are tasked with defusing a bomb represented as a circular array of integers called code. Each digit in the array corresponds to a specific part of the bomb's mechanism. The defusing process involves transforming this array into a new array called result based on a given integer k, which acts as a key. The transformation rules depend on whether k is positive, negative, or 0. If k is greater than 0, each element in the result array is the sum of the next k elements in the circular array, starting from the current index. If k is negative, the sum is taken from the previous k elements, in reverse order. If k equals 0, all the elements in the result array are simply replaced with 0. The circular nature of the array means that when you go past the last index, you wrap back around to the beginning, and similarly, if you go before the first index, you wrap around to the end. Your task is to implement a function that performs this transformation and returns the resulting array. The input to the function consists of two parameters, the code array and the integer k. The code array has a length between 1 and 100, and each element in the array is an integer in the range from -10,000 to 10,000. The key, k, can be any integer between -100 and 100. The output of the function is a list of integers, which represents the transformed result array after applying the given rules. To understand how this works in practice, let's look at some examples. In the first example, the input code is 5, 7, 1, 4, and k is 3. Here, to compute the result array, we sum the next three elements for each index in a circular manner. For instance, when I equals 0, the next three elements are 7, 1, 4, so result 0 is 7 plus 1 plus 4, which equals 12. For the same example, when I equals 1, the next three elements are 1, 4, 5. Notice here that the sum wraps around the array, so after reaching the end of the array, we continue from the beginning. Adding these values gives result 1 as 1 plus 4 plus 5, which equals 10. Similarly, for I equals 2, the next three elements are 4, 5, 7, and their sum equals 16. Finally, for I equals 3, the next three elements are 5, 7, 1, and their sum equals 13. This gives the final output of 12, 10, 16, 13. In another example, if k is 0, such as when the input code is 5, 7, 1, 4, and k equals 0, the rule states that every element in the result array is replaced with 0. Therefore, the output is simply 0, 0, 0, 0. Now consider a case where k is negative. In this example, the input code is 2, 4, 9, 3, and k equals -2. Here, since k is negative, we sum the previous two elements for each index, moving in reverse order. For I equals 0, the previous two elements are 3, 9, wrapping around the array, so result 0 is 3 plus 9, which equals 12. For I equals 1, the previous two elements are 2, 3, and their sum equals 5. For I equals 2, the previous two elements are 4, 2, and their sum equals 6. Finally, for I equals 3, the previous two elements are 9, 4, and their sum equals 13. This results in the output 12, 5, 6, 13. There are a few constraints and edge cases to keep in mind. First, the length of the code array is always at least 1, so if it has only one element, the result array will always be 0, regardless of the value of k. If k is greater than the length of the array or its absolute value is very large, the circular nature of the array ensures that indices wrap around correctly, so elements are reused as needed. For smaller absolute values of k, only the required number of elements are summed. Additionally, when k equals 0, the result array is straightforward, with all elements replaced with 0. These considerations ensure that the function works correctly for all valid inputs. To solve this problem, we are working with a circular array called code, where each element represents a digit of a bomb's code. The task is to transform the array based on the value of k. When k is greater than 0, we replace each element with the sum of the next k elements, wrapping around the array as needed. If k is less than 0, we instead sum up the previous k elements, again handling the circular nature. If k is 0, every element becomes 0. The circular behavior means that when we go past the last index, we wrap back to the beginning, and modular arithmetic helps manage this. Now, while our goal is to compute this transformation efficiently, let's first consider a brute force approach to understand the problem better. In this method, for each index, we manually calculate the required sum by iterating through the next k or previous k elements using nested loops, applying modular arithmetic to handle wrapping. This approach is straightforward but inefficient for large arrays or large values of k due to its time complexity of O and asterisk k. In the brute force approach, modular arithmetic plays a key role in ensuring circular wrapping. For instance, when summing the required elements, we use modulo %n to cycle through indices, even if they go out of bounds. However, the inefficiency stems from the fact that for each element in the array, we recalculate the sum from scratch, resulting in redundant computations. To address this, we consider an optimized strategy, the sliding window approach. This method avoids recalculating sums repeatedly by maintaining a running sum of the required k or k elements. We start by computing the initial sum for the first index, then slide the window across the array. As we move the window, we update the sum by subtracting the outgoing element and adding the incoming one, again handling circular wrapping with modulo arithmetic. This drastically reduces redundant calculations. The sliding window approach achieves a linear time complexity of O, n, making it significantly faster and more suitable for larger inputs. The sliding window approach is not only faster but also leverages the continuous nature of the sums to eliminate unnecessary recomputation. By efficiently managing the window with modulo arithmetic, we can process each element in constant time during the traversal. While the implementation is slightly more complex due to the need to handle circular indexing, the performance improvement makes it worthwhile. This approach also handles edge cases seamlessly. For example, when k is 0, we can directly return an array of zeros since no computation is needed. If the input array is empty, the function simply returns an empty array. Additionally, for large values of k, we use modular arithmetic to avoid iterating over unnecessary elements, keeping the solution efficient even in edge scenarios. These considerations make the sliding window method the optimal choice for this problem. Now, let's look at the Python implementation of the sliding window approach. First, we handle the edge case where k is 0 by immediately returning an array of zeros. For other values of k, we initialize a result array and calculate the initial window sum. Depending on whether k is positive or negative, the starting and ending indices of the window are set appropriately, taking care of circular wrapping. Using a loop, we compute the initial sum of k elements. Then, for each index in the array, we update the result array with the current window sum and slide the window forward. This involves subtracting the element that is leaving the window, incrementing the window indices, and adding the new element that is entering the window. Modular arithmetic ensures the indices stay within bounds. At the end of the traversal, the result array contains the transformed values, and this implementation handles all edge cases efficiently, achieving the optimal performance. In summary, we explored two approaches to solve the problem, the brute force method and the sliding window method. While the brute force approach is intuitive, it suffers from inefficiency due to its O and *k time complexity, making it impractical for large inputs. The sliding window approach, on the other hand, optimally reduces redundant computations by maintaining a running sum, resulting in a linear time complexity of O, n. By leveraging modular arithmetic and pre-computing sums, we efficiently handle the circular nature of the array in edge cases like k = 0 or large k values. This makes the sliding window approach not only the most efficient but also the most practical solution to the problem. To solve the problem of transforming a circular array based on the integer k, it's important to first understand the circular nature of the array. In a circular array, the indices wrap around, meaning that if you go beyond the last index, you return to the first one, and if you go before the first index, you wrap around to the last. This behavior is crucial when summing elements as it allows us to treat the array as if it repeats indefinitely. Next, we need to address a few edge cases. If k is 0, the transformed array will contain only zeros because no elements are summed. If the array is empty, the result is naturally an empty array as well. For cases where k is larger than or equal to the length of the array, the sum wraps around multiple times, but the circular property ensures that we only process valid indices. Once these considerations are clear, we initialize our variables. The length of the array, n, is stored for convenience, and we create a result array of the same size as code, initialized to 0, which will store the transformed values as we calculate them. Now, let's dive into the iterative process. To compute the transformed values, we loop through each index I in the array code. At each step, we calculate the sum of either the next k elements if k is positive, or the previous k elements if k is negative. The calculation of these sums relies on modular arithmetic to handle the wrapping of indices due to the circular nature of the array. For k greater than 0, we start from the index I plus 1, %n and sum the next k elements, ensuring that we stay within bounds. For k less than 0, we begin at I1 plus n, %n and sum the previous k elements, moving backward and wrapping the indices as needed. After calculating the sum for a given index, we update the corresponding position in the result array with the computed value. Once all indices are processed, we return the result array, which now contains the transformed values. There are a few key insights that help us solve this problem efficiently. First, modular arithmetic is essential for navigating the circular array and ensures that we can correctly access indices within bounds regardless of whether k is positive or negative. While the straightforward way to compute the sums involves iterating through the circular array for each index, resulting in a time complexity of O n asterisk k, this becomes inefficient for large arrays or large values of k. Instead, we can use a sliding window optimization. With this approach, we maintain a running sum of the elements within the current window. For k greater than 0, as the window slides forward, we update the sum incrementally by adding the next element and removing the previous one. Similarly, for k less than 0, we slide the window backward, making analogous updates to the sum. This optimization reduces the time complexity to O n, making the solution much more scalable. To implement this solution, we rely on a few fundamental data structures and operations. The input array code is the primary data structure, and we create a new result array to store the transformed values. Conceptually, the sliding window technique is employed to maintain the running sum of elements within a fixed range, enabling efficient updates in constant time. Modular arithmetic plays a critical role here, as it allows us to handle the circular behavior of the array seamlessly. For example, I plus x, %n is used for wrapping indices forward when k greater than 0, while I x plus n, %n wraps indices backward when k less than 0. Summation is another key operation, and while a brute force approach iterates through the array repeatedly, the sliding window method optimizes this process. Finally, robust handling of edge cases such as k equals 0, empty arrays, or very large values of k ensures the solution works correctly in all scenarios. These techniques together form an efficient and comprehensive approach to solving the problem. This Python implementation solves LeetCode problem 1652, Defuse the bomb, which involves transforming a circular array based on a given integer k. The function decrypt takes two inputs, code, a list of integers representing the circular array, and k, an integer that specifies how the transformation should occur. First, the function computes the length of the array, n. It initializes the result list with zeros, which will hold the transformed values. If k is 0, the function directly returns the result filled with zeros, as no transformation is needed. For positive k, the function iterates through each index I of the array and calculates the sum of the next k elements, wrapping around circularly using modulo arithmetic. For negative k, the function sums the previous k elements similarly by adjusting the indices appropriately. The transformed values are stored in the result list and returned as the final output. This implementation ensures efficient handling of both positive and negative k values, utilizing the circular nature of the array effectively. Here, we start by importing the necessary utility package and defining the solution class. Inside the solution class, we create the decrypt method, which takes two parameters, an integer array called code and an integer k. The method will return a new integer array that represents the transformed version of the input array. First, we determine the length of the input array and initialize an empty result array of the same size, which will eventually hold our output. If k is 0, we quickly return the result array as it is, since no transformations are needed. Now, if k is positive, we loop through each element of the input array. For every element, we calculate the sum of the next k elements in a circular manner. To achieve this, we use modular arithmetic to wrap around indices when they exceed the array bounds. The computed sum is then stored in the corresponding position of the result array. On the other hand, if k is negative, the logic changes slightly to account for the previous elements instead of the next ones. For each element in the array, we calculate the sum of the previous k elements by iterating backwards. Since we are working with negative indices, we again use modular arithmetic to ensure the indices remain within bounds by adding the array length to the shifted index. Once the sum is computed, we store it in the result array at the current index. Finally, after all elements have been processed, we return the result array containing the transformed values. This implementation efficiently handles both positive and negative values of k, leveraging the modular operator for circular indexing. In this problem, Defuse the bomb, we are given an array called code and an integer k. The goal is to transform the array into a decrypted version based on the value of k. For positive values of k, each element in the output is the sum of the next k elements in the array, while for negative values of k, it becomes the sum of the previous k elements. If k is 0, all elements in the output are simply set to 0. For instance, with a positive k of 2 in the input array 5, 7, 1, 4, we calculate the next two elements for each index, wrapping around the array using modular arithmetic, and populate the result. Let's break this process down step by step to see how it works. To begin, we initialize the length of the array n as 4, and create a result array filled with zeros, 0, 0, 0, 0. Since k is greater than 0, the task is to sum the next two elements for each index. For index 0, we take the elements at positions 1 and 2, which are 7 and 1, and add them together to get 8. We update result 0 to 8. For index 1, we calculate the sum of the elements at positions 2 and 3, which are 1 and 4, resulting in 5. This value updates result 1. At index 2, we wrap around the array, summing the elements at positions 3 and 0, which are 4 and 5, giving 9. Finally, at index 3, we sum the elements at positions 0 and 1, which are 5 and 7, yielding 12. After these calculations, the final output array becomes 8, 5, 9, 12. Now, with a negative k, such as k equals -2, we instead sum the previous two elements for each index. Starting with the input array 2, 4, 9, 3, we initialize n as 4 and the result array as 0, 0, 0, 0. For index 0, we calculate the sum of the elements at positions 3 and 2, which are 3 and 9, resulting in 12. We update result 0 to 12. For index 1, we sum the elements at positions 0 and 3, which are 2 and 3, yielding 5, and update result 1. This demonstrates how the process works for negative values of k, where we move backward in the array. Continuing with the negative k example, for index 2, we sum the elements at positions 1 and 0, which are 4 and 2, giving 6. We update result 2 to 6. For index 3, we calculate the sum of the elements at positions 2 and 1, which are 9 and 4, resulting in 13, and update result 3. By the end of this process, our output array becomes 12, 5, 6, 13. This approach ensures that we handle the circular nature of the array correctly by using modular arithmetic. For cases where k is negative, the summation always moves backward, wrapping around as necessary. When k is 0, the output is straightforward, all elements in the result array are set to 0. For example, with the input array 10, 20, 30, 40, and k equals 0, we directly initialize the result array as 0, 0, 0, 0. There's no computation required since the problem specifies this behavior explicitly. To summarize, modular arithmetic is key to managing the circular nature of the array, and the time complexity of this approach is O in k, where n is the length of the array. This solution effectively handles all edge cases, including positive, negative, and 0 values of k. To analyze the time complexity of our solution, we begin by looking at the initialization steps. First, the length of the input array, n, is determined, which is a simple operation taking constant time, O1. Next, we initialize the result list with n zeros, which requires allocating space proportional to the size of the input, so this step takes n time. Now, if the value of k is 0, the function directly returns the result list without any further computation. This involves only a constant time check and return operation, making this case 1. However, when k is positive, the function enters a loop that iterates over each index I of the array code. For each of these n iterations, the solution computes the sum of k elements within a specific range. Computing this range involves modular arithmetic to ensure circular indexing, and the summation itself iterates over k elements. Therefore, each of these iterations takes k time, leading to an overall time complexity of n*k for this case. Now, let's examine the scenario when k is negative. In this case, the solution still iterates over all n indices of the array code. For each index I, it calculates the sum of k elements, but this time the range is defined differently due to the negative value of k. Specifically, the range goes from I plus k %n to I %n, again employing modular arithmetic to handle circular indexing. The summation is performed over the absolute value of k, denoted as k, which is equivalent to k for negative values. As with the positive k case, this summation takes k time for each of the n iterations. Therefore, the overall time complexity remains n*k, regardless of whether k is positive or negative. The nested structure of the iteration is the dominant factor in this analysis, leading to the same time complexity in both cases. Now let's shift our focus to the space complexity of the solution. The input array code has a size of n, and the result array, which is used to store the output, also has a size of n. Beyond these, the algorithm does not employ any additional data structures that grow with the input size. The summation within the loop uses a generator expression, which operates in constant space since it only requires storage for the iteration variables. Therefore, the auxiliary space usage is 1. Combining these observations, the overall space complexity of the solution is n, driven primarily by the space required to store the result array. To put this into perspective, let's compare the current solution with other approaches. A brute force method would involve explicitly iterating over the relevant elements for each index without leveraging modular arithmetic. While this naive approach still results in n*k time complexity, it might also incur additional space overhead due to intermediate computations, making it less efficient. Another optimization, using the sliding window technique, could further improve the time complexity. With this approach, after computing the sum for the first index, subsequent sums can be derived in constant time by adjusting the window, reducing the overall time complexity to n. In conclusion, our current solution, while not as optimized as the sliding window method, strikes a balance between simplicity and efficiency. In the best case, where k is 0, the time complexity is n, due to initialization alone. In the worst case, when k is large, the time complexity is n*k. The space complexity remains n in all cases, as the solution does not rely on additional memory beyond the input and output arrays. One of the most common mistakes in this problem is not handling circular indexing correctly. Since the array is treated as circular, indices that exceed the array bounds need to wrap around using modular arithmetic. For example, instead of accessing an out-of-bound index, you would use I %n to ensure it cycles back within the valid range. This is a critical part of the problem, as failing to account for the circular nature often leads to incorrect results. Another error is misinterpreting the case when k equals 0. The problem explicitly states that the entire array should be set to zeros in this scenario, but some solutions overlook this edge case. To address it, you should always check for k equals 0 as a special condition. Additionally, relying on a brute force approach to sum the next k elements for every index can be problematic for larger input sizes. This method has a time complexity of n*k, which is inefficient. Instead, you can use a sliding window technique to reduce the complexity to n. Finally, off-by-one errors in range calculations are a frequent pitfall. For example, you might accidentally include or exclude the current index in the summation. To avoid this, clearly define the desired range and adjust your loop or calculations accordingly. Another important variation to handle is when k is negative. In this scenario, instead of summing the next k elements, you need to sum the previous k elements. Failing to reverse the direction of the summation window for negative k values results in an incomplete solution. Addressing this requires careful handling of the indices to ensure you correctly sum the leftward elements. From an interview perspective, this problem is a great test of your ability to recognize patterns. Specifically, it assesses your understanding of modular arithmetic for circular arrays and the sliding window technique for optimization. Both of these are common patterns in array-based problems. It's also crucial to anticipate and test edge cases, such as when k is 0, 1, negative, or larger than the array size. Small arrays, like those with just 1 or 2 elements, can also introduce edge cases that need careful handling. In terms of optimization, interviewers may ask you to first implement a brute force solution and then optimize it. Be prepared to discuss the trade-offs between O, n asterisk k, and O, n approaches. Finally, follow-up questions might introduce variations, such as non-circular arrays, weighted sums, or conditions where certain indices are excluded from the summation, so it's helpful to think about how your approach can be adapted. To deepen your understanding of this problem, it's helpful to explore related problems that build on similar techniques. For instance, LeetCode 209, minimum size subarray sum, focuses on the sliding window technique, which is critical for optimizing some calculations. Another related problem is LeetCode 918, maximum sum circular subarray, which also requires handling circular arrays effectively. For problems centered on optimizing subarray calculations, LeetCode 560, subarray sum equals k, is a great example. Finally, LeetCode 862, shortest subarray with sum at least k, introduces sliding window constraints, which offer additional challenges. By practicing these problems, you'll strengthen your grasp of the key strategies required for this problem, like modular arithmetic and sliding windows, while also preparing to tackle more advanced variations. When solving this problem, there are a few alternative approaches you can consider. The first is the brute force approach, where you calculate the sum of the next k or previous k elements directly for each index. This approach is straightforward and easy to implement, but it has a time complexity of O, n asterisk k, making it inefficient for larger arrays. A more efficient method is the sliding window technique. Here, you maintain a running sum of k elements and update it by adding one element and removing another as the window moves along the array. This reduces the time complexity to O, n, though it requires careful implementation to handle edge cases and modular indexing. Another option is the prefix sum array. In this approach, you pre-compute a prefix sum array, which allows you to calculate range sums in constant time. While this method also has an overall complexity of O, n, it may require additional memory and extra care when dealing with circular indices. Each of these approaches has its own trade-offs, so the choice depends on the specific constraints and requirements of the problem. Great work! Today, we learned how to solve problem number 1652, defuse the bomb, by leveraging sliding window techniques and understanding circular arrays. Remember, mastering these concepts will help you tackle a wide range of array-based problems. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!